A motherboard has many different hardware components that the CPU needs to interact with. Typically, there is also a number of external devices that the CPU needs to communicate with as well. To learn how this works, we're going to refine our knowledge of what physical memory is, as well as introduce the concept of memory mapped input and output. We're also going to talk about what happens when your CPU tries communicating with hardware that doesn't exist, or you don't have proper permissions to access. If you have prior experience with virtual memory, page faults, and segmentation faults, this last topic will be similar to that, but will be operating at the level of the physical address space instead of the virtual address space. Let's take a look at the hardware components that we have on our motherboard. In the top center, we have our CPU, which is responsible for executing instructions and performing computation. Over here, we have 4 RAM sockets that each have a RAM module inside of them, which we can add and remove. The RAM modules are responsible for storing the majority of the data that our programs use while our computer is running. The memory controller is responsible for routing data back and forth between the RAM and the CPU. It also provides a slower connection out to the I/O controller, which in turn connects to all of the ports out here, as well as a number of the other chips on the board to allow the CPU to access the other hardware components that we have here. The Super I/O controller is responsible for controlling the internal speaker, which can make beeping noises from our motherboard, as well as these LED lights. Down here we have the read-only memory chip, which is where all the firmware programs that we have written in the previous videos have been loaded. When the CPU first turns on, it's going to run whatever program is located on the ROM chip here. In the future, we'll be writing a BIOS, which is a special type of firmware program, which is responsible for performing different types of initialization during the boot process before locating, loading, and transferring control to whatever bootloader or operating system is installed on the computer. Over here we have the CMOS chip, which is used to store various settings that can be used by the BIOS. Up here we have the power management unit, which is responsible for managing the flow of electricity between different locations on the motherboard, as well as handling the reboot and shutdown process. Lastly, on this side here, we have a number of ports that can be used to connect to different types of external devices, such as terminals, keyboards, external hard drives, USB drives, and so on. In order to send information to any of these hardware components, we need to know where we're sending that information to. In the real world, when you're sending a letter or package to somebody, you need to know that person's address in order to send it to the correct location. On your motherboard, when your CPU wants to send information to a particular hardware component, it's going to need to know the address of wherever it needs to send that information. Unlike the real world, where most buildings have one address, the hardware components on a motherboard are more like apartment buildings, where there's a whole range of addresses that belong to the same building or same hardware component. On the right side of the screen, we have the physical memory map. This tells us which ranges of addresses belong to which hardware devices. So for example, the address range from address 0 up until this address right here belongs to RAM module 0, which is this RAM module in this location here. We can also see several other address ranges that belong to the other components that we've talked about so far. This region called GBS headers right here, if we zoom in on it, we can see that there's 4 rows of information that belong to each one of our port numbers over here. Working with memory mapped I/O with external devices is a little bit more complicated, and we're going to come back to it in a future video. For now, we're going to take a look at simpler examples of memory mapped I/O with controlling the LED lights that we have right here and with the power management unit. When this motherboard powers on, the CPU light right here is going to turn on automatically. It does this for reasons that we'll learn about in a future video on how to write a BIOS. But for now, let's just write a program which is going to turn this light off using memory mapped I/O. If we open up the computer datasheet, we can take a look at the section on indicator lights. We can see that the CPU light is controlled using this address right here. In particular, if we write a 1 to this address, then it's going to turn the light on, and if we write a 0 to this address, then it's going to turn that light off. Here we have a small program that loads that address into the T0 register, and then we're going to use the store byte instruction to store the value of 0 into the address that we have right here. and then we're just going to cause the program to pause. And so if we run our program, we can see that our CPU light turns off. If we want to modify our program now to perhaps turn on the boot light, we can take a look to see what address that is at. And so here we can see that this is the address for the boot light right here. Now we have the small program that takes the address for the boot light and puts it in the T0 register, puts a 1 in the T1 register, and then uses store byte to store that 1 into the address for the boot light. And so if we come back to our motherboard and run our program, we can see that both the CPU light turns off and the boot light turns on. Let's run this program again, but this time we're going to closely watch what's happening in memory. The address that we have right here is the address of the boot light, and we can see that that address is located right here. If you recall from our previous videos, each line in the memory view contains 4 bytes of data. And the address that we have over here refers to the address of the last byte in that row. If we add 1 to this address, that'll give us the address of this byte right here. If we add 2 to this address, that'll give us this byte. And if we add 3 to this address, that'll give us this byte right here. So for example, if we add 3 to this number right here, that'll give us this number right here, which is the address of our CPU light. Now the address for the CPU light currently shows a 1 right here, and it shows a 1 right here, indicating that the CPU light is on. The address for the boot light, which is the address for this byte right here, currently shows a 0, and so we can see that the boot light is currently off. Let's go ahead and step through the first couple instructions here. These 2 instructions right here correspond to the load immediate pseudo instruction that we have right here. If you don't recall how pseudo instructions work, you can review that in one of the previous videos. The load immediate instruction is going to take the value that we have right here and store it in the T0 register, and so we can see that that address is located right here now. Next up, we have the store byte instruction, which is going to write a single byte containing the value 0 into the address that is currently held by the T0 register, which is this address right here, which is the address for our CPU LED. So if we step through the next instruction, we can see that now our CPU light has turned off and we have a 0 located right here. If we step forward a couple more times, we can load the address for the boot LED right here. So that's now located in our T0 register. We're going to load a 1 into the T1 register now with this instruction right here. And then we're going to do the store byte again, but this time we're going to be storing a 1, and it's going to be for the address of the boot light. And so when we step forward again, we can see that we have a 1 that shows up here in the byte for the boot light, and we have the boot light has turned on over here. If we want to shut down our computer, we can do so by communicating with the power management unit. And so that's located right here on the motherboard. And if we take a look at the computer datasheet, we can see that we have a power mode register, which is located at this address right here, which we can also see is right over here. And if we write the power mode for shutdown, which is the number 2 right here, if we write that 2 to this address right here, that's going to cause our computer to shut down. So this program right here can do just that for us. And so if we run it, we can see that our computer is now shut down. The last topic that we are going to cover is the physical memory protection system. This will allow us to answer the question, what happens when we access a physical memory address that isn't actually associated with any real hardware? Or what happens when we access a particular piece of hardware in a manner that it's not supposed to be accessed? For example, if we are trying to write to a read-only memory chip. The physical memory protection system in RISC-V is managed by creating a number of physical memory protection regions, like we can see in this diagram right here. Each one of these regions covers some portion of the physical address space. Each region also has a configuration register which defines the properties of that region. In particular, the configuration registers tell us the execute, write, and read permissions for each one of our memory regions. So here we can see that the RAM modules all have execute permissions, write permissions, and read permissions. The read-only memory region has execute and read permissions, but no write permissions. And the platform and external devices are readable and writable, but not executable. Platform devices are all the devices that we have that are physically on the motherboard, and external devices refers to the devices that get plugged into the motherboard. You'll notice that the read-only memory region is both executable and readable. This is because the read-only memory region must include the entire firmware program that is going to run when the motherboard first turns on. And so it's going to need both the code part of that program, which must be executable, and the constants and string literals, which must be readable. In the previous videos, we have talked about the regular registers, which we can see over here, but each CPU also has a large number of additional registers, which are used to configure and control all sorts of different things. And these are the control and status registers. We can see them by clicking this button right here and scrolling down. If we open this back up again, all of the information that we see in these PMP adder registers down here defines the addresses that mark the boundaries between each of our physical memory protection regions. And the PMP CFG registers right here contain all of the configuration information for our physical memory protection regions. Later on, we will learn how to manually modify the control and status registers, and that will give us control over all the information for the physical memory protection regions. For now, however, we're just going to let the emulator do its default behavior, which is to pre-initialize the registers down here with reasonable defaults to give us these settings that we see at the moment. This program up here is going to perform a write to this memory address right here, which we can see is inside of the ROM region. And since the read-only memory region does not have write permissions, it's going to generate something called an access fault. So let's go ahead and run the program. We can see that this message pops up, which lets us know that an access fault occurred. Anytime that you read, write, or execute memory at a particular location that does not have read, write, or execute permission in this table right here is going to trigger an access fault to occur. The physical memory protection system is analogous to the protection provided by paging that you might have learned about in an operating systems course. The key differences are that the physical memory protection system operates on physical addresses instead of virtual addresses. The location of the permissions is located in these control and status registers instead of page table entries. And lastly, when faults occur, we generate an access fault if it's a physical access violation, and our firmware can then handle that access fault in whatever custom way it chooses to. Whereas with a access violation that occurs with paging, we're going to generate a page fault, and the operating system is allowed to handle that situation in whichever way it finds useful, which is often to generate a segmentation fault and send the seg fault signal to the process that generated the violation.